Okay, so what we're going to take a look at today is going to be a brief look at Newton's law of universal gravitation. So we're going to be dealing with the big gravity equation. Up to this point we've dealt with gravity near the surface of the Earth. We're used to the force of gravity being equal to mg. Okay? What we're going to learn now is that away from the surface of the Earth, and in fact, in general, the force of gravity is equal to G, capital G, times the mass of object 1 times the mass of object 2 divided by the distance between them squared. Okay? So if we've got an object here and an object here, then that distance would be r. It's the distance just between the two objects. Okay? So, one of the first things that we're going to look at is actually taking a look at how we get our values, what we're used to, this little g, where that guy comes from. So if I take a look at an object that's falling, say if I take this washcloth I'm using as an eraser and I let go of it, it begins falling. And it falls at g, as we have talked about before. So if I draw a free body diagram of that, this is my washcloth. It feels a force mg that we're used to downwards. Well, in this case, mg was just shorthand for force of gravity. Let's take a look at this larger equation and see what we end up with. Now, when we deal with gravity, and we'll talk about it in class, but we deal with basically the center of mass of an object. So, if I take the washcloth, I basically go from the middle of the washcloth, or middle of the piece of chalk, or middle of me if I were falling. So I could imagine that it's the core of me that's falling. I'm also going to compare that to when I'm dealing with the Earth. This is one of the things Newton found. We can imagine that the Earth is just a point particle, and that all of its mass is located here. So when I'm above it, like this, then that means that the distance between me and the center of the Earth is my effective r for this. And we'll talk about it more in class. Basically how that works out is you've got some mass over here and you've got some mass over here, and while they apply a force onto me, they pull me in this direction. In fact, let me put that this way. Both of those pull me that way. I'll have a component that goes this way for that one, and a component that goes this way for that one. They actually will end up canceling out all the way around because this guy's a sphere. And so there's just as much on this side as there is on this side. Those cancel out, and I end up with only a net force down towards the center of the Earth. Okay? And because of all these things where they have a tendency of canceling out from one side or another, where this is really close, where it has more of a force, whereas over here is really far away, thanks to the nature of the sphere, they'll actually cancel each other out, and we can treat it as though all of the mass were in the center of the Earth. So if I'm going to take a look at this, I could find the force of gravity on this washcloth is the only thing acting in the y direction when I drop it. And so when I apply my Newton's second law, as we've done before, sum of forces in the y, I have minus force of gravity equals my mass times my acceleration in the y. Okay. Well, what we used to do was we used to plug in mg, and we would end up with an equation that we could evaluate. What we're going to do this time is we're going to use the full force of gravity. So over here I've got mass times acceleration in the y, this guy, equals negative force of gravity, and that's going to be g times mass of the Earth, in this case, times mass of, say, the washcloth, or me, or just about anything, the mass of the object we're looking at, because this free body diagram could be just about anything. Okay, divided by how far away am I? Well, if I'm pretty close to the surface of the Earth, then that distance is about the radius, the radius of the Earth. That's how far away I am from the center of the Earth, where I'm pretending this point particle that accounts for all of the mass of the Earth is. Okay, so that's r squared, and that'll be the radius of the Earth. Okay. Well, you'll notice I have a mass term in both sides. So if it's me or the washcloth falling, we have a specific mass. That's m. And I can cancel the m because it's the same mass out of both sides, and I end up with my acceleration in the y direction is minus universal gravitational constant times mass of the Earth times radius of the Earth squared. Okay? Well, I'm going to need a few numbers here. G, big G, we have found to be 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Kind of strange units, but they go well in this equation that we had that will actually get us the correct units that we need. Okay, so that's big G. The mass of the Earth is, I wrote it down, yeah, just making certain, it should be 5.94 times 10 to the 24th kilograms. And the radius of the Earth equals, I'm used to saying 6.4, but we're going to go with 6.38 times 10 to the 6th meters. Now when I plug these values in here, you can go ahead and do that. I'm not going to waste a lot of time actually putting them in, but big G goes here, mass of the Earth goes here, and radius of the Earth goes in here, and I'm going to square that. When I evaluate this, I find out that my acceleration is equal to negative 9.73 meters per second squared. That should sound kind of familiar because it's very close to our negative 9.81 meters per second squared, which is what G, little g, is actually defined to be. You can see we're pretty close to that. I used the values at the equator of the Earth. I've also used, you can see, rounded numbers. These have only 3 significant digits. If I tacked a number of the further digits in there, I might get a little bit closer to the negative 9.81. And then there's also some weird effects from the Earth is not perfectly spherical, which means that this number will actually offset a little bit for the real value. Okay? Well, that's the acceleration due to gravity close to the surface of the Earth. And we can see what we've said before, where we said force of gravity was equal to mg. Well, that's just a simpler way, so we don't have to evaluate this guy each and every time. But this is what describes it fully, everywhere in the universe. Okay? Now, one of the nice things about this is we can actually use this to find the local g just about anywhere. We could find it on the moon, which is going to be very different from the Earth. Another one that I actually prepared the numbers for is, so the universal gravitational constant doesn't change, that's g. That's the same everywhere in the universe so far as we know. But if I look at the mass of, say, Mars, which is 6.42 times 10 to the 23rd kilograms. I've got the radius of Mars, and that is 3.40 E6 meters, so times 10 to the 6th meters, that's engineering notation. When I plug these numbers in instead, where I use the mass of Mars and the radius of Mars squared, well, I'll square it for the equation here, I'll find that the acceleration in the y direction on Mars equals negative 3.704, so 3.70 meters per second squared. And our dear friend, Dr. Wikipedia, says that the surface acceleration on Mars is 3.71. Okay, so again, there's a little bit offset for real-world values because Mars, like Earth, is not a perfect sphere. But you can see that we're getting very close to the value here. This would be close enough for any of our significant figures. So, this is where we actually get that little number that we've been using up to this point, g. And now if we're doing problems that are near the surface of Mars, for instance, we could simplify things with the force of gravity being equal to mass times 3.70 instead. Okay? As long as we don't get too far from the surface, then we're okay. As long as this r here doesn't change very much. Well, if I go up a couple of kilometers, that's not going to change this number very much at all. In fact, I'd have to go up about 10 kilometers for it to actually have an influence on the number that I'm using to calculate that. So that's one of the reasons why we can simplify things. As long as we're staying close to the surface of a big body like the Earth or Mars, we can just use g instead of having to calculate it out with this all the time. Now when we start dealing with things in outer space where they go very long distances, these r's start to change, and we'll have to use the full force of gravity instead of using the simplified mg.